and this week's video is going to be all about finding the absolute minimum or maximum value of a given function. Alright, so to find the absolute minimum or maximum value, you have to know a few things for the background. So first of all, you have to know what critical points are. Now, if you already know this, just skip this section, but if you don't, I'm here to explain it. So critical points are points that are where the derivative of a function is equal to 0. So if you have a function f of x, where f prime of x is equal to 0. Now you might think, why are they called critical points, and what's so special about them? If you think about finding the maximum and minimum value, and you visualize it, right? You can have a graph that looks something like this, and say you want the maximum value, and your graph does something like this, right? At the maximum value, or even maybe such a value, right? The derivative, something that you can see, is the derivative at these values is 0. It's like the function reaches the maximum value, and it can't continue growing. It's also not decreasing because it's the maximum value. So the derivative has to be 0. Same goes for minimum values, right? So this is where critical points come from. And basically, we find critical points to give ourselves a closer range and more specific numbers to look at. So we find critical points and we use them to determine the minimum or maximum value. So this was the first thing you had to know, critical points. And the second concept you have to be familiar with is functions that are concave up or concave down, and how to identify whether the section that you're looking at is concave up or down. So basically, what concave up is when your function goes like this. It opens up to the top, right? It opens up upwards. And concave down is when your function does something like this, and it opens up downwards. And if you think about how this relates to maximum or minimum points, well, it's pretty obvious. Here, in the concave up, this is your minimum point, right? It goes from top, it hits the bottom, then goes up. That's what concave up is. Now, concave down is your maximum point. Right here, this is your maximum point. And the name can be confusing because concave up sounds like maximum because you're going up, or down sounds like minimum, but don't get these two mixed up. Concave up is where the minimum value is, and concave down is where the maximum value is over here. So this is your max, and this is your minimum value, right? And basically, how this is used is that you have all of these critical points that you have found. First of all, you have to determine whether those critical points are at a possible minimum value or a possible maximum value. And to do that, you have to figure out whether the critical points are at a section where it's concave up and they lie over here, or whether they're at a point where it's concave down and they lie over here. And then you can compare those critical points by using actual values and figure out which one is truly the maximum or the minimum. Okay, so now that we have discussed what a critical point is and what concave up or down means, we can now actually figure out what we need to do to find the minimum or maximum point. And if you think you can figure out by yourself, by all means do it, because this isn't some crazy formula, crazy procedure. It's just based on logic, and you can figure it out without somebody telling you how to do it. And this is an approach to finding your maximum or minimum absolute point, right? But this approach, you first have to find the derivative of f of x, and I put this step into brackets because actually the first step is finding your critical points, but in order to find your critical points, you have to find the derivative. But just in case, I just put it there so you don't forget to use the derivative for your critical points. So you get your derivative, you find your critical points, so when your derivative is equal to 0, and then you determine whether f of x, so the function, is concave up or down on your critical points. And once again, concave up is where the function goes like this, and that is your minimum value. Well, possible minimum value. And concave down is when your function opens downwards. It's when it opens downwards, and that's your maximum value, right? And lastly, it can be so that your function has multiple points that go like this. So for example, you can imagine a function that goes like this and this and this, right? And you have all of these points. Now, I don't know how realistic this function is, but everything is possible. You have all of these points where the derivative is equal to 0, where there are critical points, and where your function goes concave up or down. So once you have determined your critical points, and depending whether you're looking for the minimum or maximum, you know whether to take the ones over here, so the ones that are concave down and looking for the maximums, or the ones that are on the bottom, right? So now you have to compare all of them, like actually type in the value of y at a given x at a given critical point and find which one is the maximum. And that's the final step. So now let's look at two examples of finding minimum or maximum values for the whole domain of the function, so the absolute minimum or maximum value. And I encourage you to do these on yourself and then come back and then check your answer. But if you're feeling lost, watch the first one. Alright, so our first example will be where f of x is equal to 3x to the power of 4 plus 4x cubed minus 12x squared plus 5, and we want to find the absolute minimum. So once again, we start by finding the critical points, where that's when the derivative of f is going to equal to 0, and the derivative of f is going to equal to what I'm writing out, just using the power rule. All right, and now we have to set this to equal to 0, and let's find a common factor. Well, the common factor here is obviously 12, so we can factorize a 12x out of here, and we can get 12x times. And then we factorize this further to get 12x times x plus 2, and then x minus 1. So our solutions for this are x is equal to 0, x is equal to negative 2, and x is equal to 1. So what this tells us is that these are the points where we have a possible maximum or minimum, right? And now we actually have to figure out where is it a maximum or minimum, where is it concave up, or where is it concave down. And to do this, we can create intervals for the functions. So I'm just going to start a new page. We had x is equal to negative 2, 0, and 1. Right? So let's do it in order. So the first interval that we can look at is negative infinity to negative 2, right? That's the lowest. Then we have negative 2 to 0. And then we have 0 to 1, and eventually 1 to positive infinity. So what we can imagine is that if we have a function, we have the derivative of a function decreasing or increasing, so here it's increasing, up until the critical point, and then it either starts decreasing, or if it's the other way around, then it's decreasing and then starts increasing, for example here, right? And in order to find this, we can simply look at the formula of the derivative, or if you're the type of person who wants to try it out, you can plug in a number in such a given range, right? So here, if we look at the formula, right, just by itself, for the range over here, we have 12x to the power of 3, and this is going to be a negative number. So we're going to have a negative, then you're going to add a positive, and then you're going to minus a negative, which is going to equal positive, But you have to consider the ranges of values that you're looking at, and considering the fact that there's another interval over here, this can suggest that the positive isn't big enough to cancel out all of the negatives. And in this case, I would actually suggest trying out a number. So for example, if you plug in, let's plug in -3 for x. And according to my calculations, that would give you -144. And what that suggests is that your derivative is negative, thus the function over that interval, it's decreasing. So you can actually put in a number, which is always going to give you the precise number, or you can just look at the function and the equation of the derivative and then figure out, but you have to keep in a couple of things in mind if you're doing it that way. So what about our second interval over here? Well, over here we have -2 that goes to 0, right? And at this point, we can test out -1. And if we put in -1, quickly do it through your head, well, that's going to give you a positive number, and your function is increasing over that interval because the derivative is positive, right? If you have a positive f prime of x, that means your function is increasing. And if you have a negative f prime of x, your function is decreasing. I hope that made sense before and I wasn't just talking about something I didn't explain. All right, so your function is increasing. Let's try it out for the domain between 0 and 1. So let's say we plug in 0.5. If you plug in 0.5, you have a negative number. That means that your f prime of x is decreasing. And lastly, between 1 and infinity, let's plug in 2. That's going to give you a positive number. That means that f prime of x is increasing. Now this is a pretty scenario because here you have something that decreases, increases, decreases, increases. So it switches, and you can imagine, for example, this could look like something like this. Decreases, increases, then decreases again, then increases, and it stops here, and then just goes up. But that's not always the case, and that's why we have to test, because sometimes a function can just have a spot that goes like this, and it doesn't mean that it's the minimum or the maximum like over here, and thus we have to test out and see. But this is a really pretty scenario, and this could be what our function looks like right over here, but once again we have to test out the values to know which is the maximum or minimum. So let's determine which of these are concave down or concave up. And concave down is when a function opens up downwards and you have the maximum, and concave up is when you have the minimum because the function opens upwards, right? And think about it. Here you have something that's increasing and then it's decreasing. So if you want to find your maximum, you have to find points that are increasing, then they reach the point, and then they start decreasing. But if you want to find the minimum, which is what we're trying to do right now, you have to find critical points that the derivative decreases and then it starts increasing. So where do we see that? Well, over here, it's decreasing and then increasing. So, and that's at -2. So we can use -2 as a point, and then it's decreasing and then increasing at 1. So the numbers we have to test are -2 and 1. All right, so, and to do this, this is really simple. You have your f of x, don't mess this up with the derivative f prime of x, and you just plug in the values into your f of x and find which one is greater between your competing values, you can say. So our critical points that are valid are -2 and when x equals 1. And if you plug this in to the equation, at -2, f of x is equal to -27. And at 1, f of x, well, that's just equal to 0. So obviously, this number is less than the other one. So this is our final absolute minimum, and our absolute minimum is at x equal -2, right? So I hope this procedure made sense. And if we look at the graph itself over here, this is exactly what we just calculated. Here is the -2, and it equals to -27, and this is our function right over there. All right, so this was the first example. This is our second problem that we're trying to solve, and our function is e to the power of -2x times x, and we want to find the absolute maximum value of this function, so its maximum value for the entire domain. And once again, we're just doing the same thing, but now we're focusing on the maximum value. And do that yourself and then check your answer. So to do this, we have to find the critical points, but first to do that, we have to find the derivative. And to find this derivative, it's a bit more complex than the previous one because you have to use the composite functions rule together with the product rule, and I would just start off using the product rule. The product rule is where you have the derivative of e to the power of -2x times x plus e to the power of -2x times 1, because the derivative of x is 1. And then you use the composite rule over here. So you have e -2x times -2x, which is just -2 times x plus e -2x, right? And then you can simplify this a bit, and you have e to the power of -2x that times -2x plus 1, because this is simplified -2x. And if we want to simplify this one last time or rewrite it in a smarter way, I would say that it's easier to look at it this way. All right, so to find the critical points, we set this to equal to 0, and the possibilities of this equaling to 0, well, think about it. Can e to the power of -2x ever equal 0? Well, no, it can't, because no matter what you make x, you're going to have a number. Even if x is 0 and you're raising something to the power of 0, that's still going to be 1. So this will never equal 0. So what we can focus on is this part over here. And in order for this to equal 0, well, you just have to make x equal 1/2, right? So our critical points are x is equal to 1/2. All right, and there's no other critical point. So we can assume that this is the maximum because that's what they're asking for, so we can assume that that is our maximum. But I would still advise to double check, because what if you found the derivative wrong? That could happen. What if it's a trick question and they want you to tell or to say that, no, there is no maximum, or no, this is not a critical point, and the function just grows and doesn't have a maximum point. So we're still going to check this critical point. Here, the only ranges that we look for are -infinity to 1/2, and then 1/2 to +infinity. And I hope these ranges make sense, because basically what you're doing is you have, this is an ugly function, you have a function that might do something like this, right? And your critical points are over here. And what you're doing by looking at the ranges is you're finding out whether it goes up or down or up before the critical point. And then if it goes up and then down, it's concave down, so it's the maximum. If you go down then up, it's concave up, so then it's the minimum, as I've already explained, but it's a good reminder always. Okay, so our derivative was e to the power of -2x times 1 minus 2x. And say we plug in -1 for this value over here, we will have f prime of x. That's going to give us what? That's going to give us a positive value, so we're going to be increasing. And then over here, if we plug in, say we plug in 1, what is that going to give us? That's going to give us a negative value, so f prime of x is be decreasing, because once again, if we're decreasing, if our derivative is negative, we're decreasing in the function, right? The slope is negative, and then the other way we're increasing. All right, so here we can for sure see that this is a maximum point because this is concave down. We're increasing, we reach a certain point, and then we start decreasing, right? We increase over here, and then we decrease over this interval. For here, it doesn't matter what the maximum is. We're just focused on finding the x value. From there, you can solve it yourself if you're interested. But what we know is that the maximum point of this function in the entire domain is at x equals 1/2. And that's how you do it. And if we want to compare this to the actual graph that we get, here we can look over here, and this is our function, right? Here, this is x equals to 1/2, and this is the maximum point here is really small, but it's still a maximum and it still counts, and it's a decimal that's around 0.184. All right, so I hope this helped, and I hope you know how to find the absolute minimum or maximum. This is a pretty similar procedure to do it in closed ranges or domains, and yeah, I hope this helped, and see you next time.